All right. So today we're solving problem 2594, minimum time to repair cars. This problem is very difficult if you haven't learned the associated approach, which is very obvious if you have done a similar problem, okay? This is one of those problems where most of us that aren't geniuses, including me, and probably statistically, the probability is it includes you, right? Us mere mortals have difficulty deriving the solution to a problem that's stated like this, okay? But if you have seen a problem that's stated like this before and you have learned the associated approach to solve it efficiently, these kind of problems are super simple because they have a very strict and constrained description, and the constraints are so constricted in terms of how the problem is described that you can almost instantly associate it with the pattern or the approach that you've learned and apply that approach to solve this problem efficiently, okay? So this is something where if you've never seen something like this before and you haven't learned the associated problem, it's almost impossible that you're going to be able to derive that within an interview. But if you have seen an associated problem before and you do understand the optimal approach, this problem is very simple and easy to solve, okay? So today what I'm going to do is I'm going to tell you what that approach is, what the patterns are to look for to know if that is the approach, and it's usually pretty obvious, and then show you a code style, right? Like a generalized form that's actually super cool and short and a little difficult to understand initially, but is definitely like, whoa, that's kind of cool. One of those kind of situations, okay? So with that said, let's go ahead and get right into it. So you're given an integer array ranks representing the ranks of some mechanics, okay? So mechanics have ranks. What does that mean? Ranks I is the rank of the ith mechanic. A mechanic with rank R can repair n cars in R times n squared minutes, okay? So you have ranks of mechanics, right? So we'll do the example here, okay? Let me make sure everything's visible. So if you have ranks equals 4, 2, 3, 1. Okay, so 4, 2, 3, 1. All right. So this mechanic has a high rank. This mechanic has rank 2. This mechanic has rank 3. This mechanic has rank 1. All right. A mechanic with rank R can repair n cars in R times n squared minutes. Okay, so, this guy has rank R equals 4. And so in m minutes, he could do his rank times the number of cars he's supposed to fix squared. So that's kind of the formula. So m equals minutes, n is the number of cars, R is the rank. So if his rank was 10, he could wash 5 cars in 5 squared 25 times 10, 250 minutes. All right, or fix that many cars. Right, so this is basically the closed form formula to determining, like, okay, I got this guy's rank. I'm going to give him this many cars. How long is it going to take him? Okay, so maybe we should just describe what these variables are. So R is the rank. N is the number of cars. And M is the number of minutes it's going to take. Okay. You're also given an integer cars representing the total number of cars waiting in the garage to be repaired. Okay, so I guess there's a bunch of cars that are, they're chilling out and they all want to get fixed. Return the minimum time taken to repair all the cars. All right, note all mechanics can repair the car simultaneously, right? So they can all use their rank and fix the cars. They're not like dependent and waiting on each other for information or something like that. All right, so since we've already, started writing out this example, let's look at what the minimum amount of time would be, okay? Now, this is one of those things where it's hard to even derive the answer without knowing the approach, right? Because it's like, how would you get 16? How would you know that's the minimum time? Well, you know it's the minimum time because 15 minutes you couldn't do it, 17 minutes you could do it, right? But it's like, how would you get the information? Like, it doesn't reveal a lot about the problem, but it says 16 minutes. So how do we know it's 16 minutes? Well, in 16 minutes, what could this guy do? What could this guy do? And what this guy do? And what this guy do? How do I state that a better way? Basically, what this problem comes down to, right, is saying, okay, in 16 minutes, if the answer is 16 minutes, well, then that means that they must be able to clean all 10 cars in 16 minutes. All right. How do we know that that's true? How do we know it's true that within 16 minutes, these 4 mechanics were able to fix all 10 cars? Well, you can figure it out by saying, well, in 16 minutes, how many cars did this guy end up doing? How many cars did this guy end up doing? How many cars did this guy end up doing? How many cars did this guy end up doing? Right? So this formula isn't really in the correct order, right? Because if it's 16 minutes, how do I even verify this information, right? That's basically what I'm getting at now. How do I verify that in 16 minutes they were able to do the 10 cars? Well, it's based on this formula, right? This guy for 4, well, in 16 minutes, how many could he do? How many could he do? So really what we need to do is figure out for each person, right? For each person, for each rank are how many cars in n minutes, or how many cars, that would be n. This is I'm doing a very terrible job today. How many cars n, how many cars n could be done in m minutes? So basically what I'm trying to get at here, and I'm doing a terrible job of it, is take this formula and we want to solve for n, okay? So this becomes n equals m over r, which means that n equals the square root of m over r. All right, so basically, I want to figure out, what I'm trying to do right now is, how do I even know that the answer is 16? Like, that's the first part of this problem. Well, what I could do is figure out, okay, in 16 minutes, how many cars could he fix? 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 Can they all fix the amount of cars necessary to get 10 cars finished in 16 minutes? Well, let's see. So for the first character, the first person can do n equals 16 over 4, which equals 2. So the first guy can do 2 cars in 16 minutes, right? Because he got 16 minutes here. His rank is 4, so he can do 4 square root at 2. So the first guy will give you 2. The second guy's got rank 2, so so the higher their rank makes sense. So the second guy can get 16 divided by 2, square root of 8, which is like 2-ish. 2, 16, 4, and 4. So 4, 5, 6, 7, 8, 9, 10. So I basically did really quick math, but if you evaluate these using this formula, you'll get these values, okay? And is that what it says here? The first mechanic will repair 2 cars. The second mechanic will repair 2 cars. The third mechanic will repair 2 cars. And the fourth mechanic will repair 4 cars. Okay, so, now, of course, the thing that's weird here, right, is that, like, when you do a square root, you're not guaranteed an integer value, right? So you might not be able to use all the time, right? Like, you could fix 2 cars, but then you don't have enough time to fix a third car, right? So you can only fix 2, right? You can't fix like 2.34 cars or whatever. So this formula, you actually need to take it and push it down. Okay, so basically all this means is, we need to figure out if the time's good, we need to figure out how many cars each person can fix. If the sum of all that is greater than the time, then we're good, right? And we need to do the floor divide because you can't fix 0.3 cars or whatever. So it's the floor divide of the square root of m over r. Okay, that's the number of cars each mechanic can fix. So then the number of cars we totally fixed is you just take the sum of each rank inside of ranks of m over r. All right, so that's how you figure out how many cars you could fix for any given minute, right? So if you give a minute, the amount of cars that you're going to be able to fix is the sum of the square root of that minute over r for all the values. right? Makes sense? Kind of, right? This is just the fact. It's just the fact of this formula. And then saying, okay, how many cars could you fix in a given minute sentence, right? It's based on this here. I don't know what else to tell you, right? That's just basically what the formula is. But how do we use this information to derive a solution? Because now we know if it's possible, right? If it's possible, then this information, let me make this a little bit bigger, will be greater than or equal to the number of cars that there are, right? This is basically the idea here, right? For any M value, right, I can make it work. I can say, okay, you gave me 16 minutes. In 16 minutes, this value is the total number of cars that I could fix with all my mechanics. Is that greater than the number of cars? Then it works. If it doesn't, then it doesn't work, right? If you give me 5 minutes, I tell you the number of cars I can fix in 5 minutes, and it's less than the number of cars, then it doesn't work, right? So from this solution, we can basically determine for any M as an input, we can determine, can we fix enough cars? Okay, so basically that's a formula, right? That's another formula based on this, right? Because you know our R value is known, right? For all the R's, we know how to do the square root operation, we know how to floor divide, and we know the number of cars that we have. So this is a function in terms of M, right? So we'll call this function f of M equals this. So f of M equals, and then we're going to expand this out even more because why not? Right, so this is our formula for determining for any M value, right? Can we evaluate, can we fix enough cars given the number of cars that we're given in the situation, right? And so that's how we knew with 16 if it worked, right? Because we have M equals 16. So we take 16, we put it in here, we sum it all together, we say, is it bigger than cars? Yes, it works. But how do we find that 16 value? Well, this is where the pattern becomes obvious. Not obvious, but this is where the approach, given the pattern, makes sense. Okay? Whenever you have a question where it's like, find the smallest where it works. Find the smallest where it works. Okay, so here, what you're trying to do, you're trying to find the smallest number, you're trying to find the least number of minutes where you can fix all the cars, right? So find the smallest where it works. That's the first kind of situation that you see in this problem. The second one is, it either works or it doesn't. Okay, now this might sound kind of weird, but basically the idea is like in this formula, when I give an M, it either works or it doesn't work, right? Either it's greater than cars or it's not greater than cars. There's no like weird in between situation. There's no weird extra conditions. It's literally just one variable. I give you M and I can tell you if it works or if it doesn't work, right? Based on the thing. So it's basically it either works or it doesn't work based on the value. Meaning, I'm trying to find M, right? I'm trying to find the smallest M where this situation works, right? And it only depends on M, right? I can figure out if this works based on the M value. I just plug in this formula and it tells you, okay? And then the third thing is if it doesn't work for a value, it doesn't work for any value greater. My handwriting is so terrible. Okay? If it doesn't work for a value, it doesn't work for any value greater. What does that mean? That basically means if it doesn't work for M, it's not going to work for M plus 1. Does that make sense? What I'm saying is, if it doesn't work for one value, it's not going to work for any value that's greater than it, right? If I can't do it in 10 minutes, no, wait. It's not going to work for any value smaller than it. And in this situation, right, if it doesn't work for 10 minutes, it's not going to work for 9 minutes, right? If I can't do it with 10 minutes, what does that mean within the context of this problem? It means I need more time, right? Because I'm trying to make this as big as possible. So to make this bigger, I need m to be bigger because m is in the numerator, right? That's just the mathematical approach to this, right? But logically it makes sense. It's like, okay, I have this many mechanics. They can do it in this amount of time, each car. And then I say, okay, can you do it in 10 minutes? And I say, no, I can't. With the situation I have, with the mechanics that I have, with the rank that I have, I can't I keep saying clean. I can't fix all your cars in 10 minutes. So then they say, okay, well then can you do it in 9? It's like, no, if I can't do it in 10, I can't do it in 9. If I can't do it in 9, I can't do it in 8. If I can't do it in 8, I can't do it in 7. If I can't do it in 10 minutes, I can't do it in any time that's less than 10 minutes. Right? But it's not true the other way, right? If I can do it in 15 minutes, right, maybe I could do it in 14, maybe I could do it in 13, maybe I can do it in 12, right? But it's definitely the case that if I can't do it in a certain amount of time, I can't do it in less time, all right? So what is the beauty of that solution? What does that allow us to do then? Well, if you have a situation like this, let's imagine a scale where we have all these different times that we could try. All right, so imagine we knew, for example, 0, 5, and 10, okay? And I'm trying to figure out, can he do it in 5 minutes? Can he do it in 10 minutes? Can he do it in 0 minutes, okay? Meaning, imagine these were minutes, right, on a scale. And if I did this formula and I put in 5, and I put in 5 here, and I found out that it was less than cars and it didn't work, what does that mean? That means that everything to the left won't work. If I can't do it in 5 minutes, I can't do anything else that's less than 5. All right, so I can automatically exclude all these values, right? And then I could try here. I could try at 7.5, and I say, okay, does it work for 7.5? Oh, if it works for 7.5, then I can exclude all these values, right? Because it'll definitely work for them, right? If it works for me here, it'll definitely work with more time, right? That's the same thing. Another way of looking at this logically is saying, okay, if I have a bunch of mechanics and a bunch of ranks, and someone says, can you do it in 15 minutes? I'd say yes, right? If I could do it in 15 minutes, they'd say, okay, can you do it in 20 minutes? Yeah, if I can do it in 15 minutes, I can definitely do it in 20 minutes, right? And if I can't do it in 7 minutes, I definitely can't do it less than 7 minutes. So what does that allow us to do when we think of that logically? Is that we can quickly determine times that work and don't work based on the kind of inference, right? Based on the effect of that idea. So how this basically works, right, is let's draw another one of these stupid things. If we try any value, right, let's say, can we do it in this amount of time? If the answer is yes, well, then you can do it on any greater amount of minutes, right? If I can do it at X minutes, I can do it anywhere else here. And I'm trying to make this as small as possible. So I don't need to check the rest of these values because if it works for this, it'll work for anything greater, right? It's kind of the invert or the converse. I can't remember. Been a long time. If it doesn't work for any value, if it doesn't work for a value, it doesn't work for any value smaller. And on the flip side, right, if it does work for a value, it definitely works for any value larger, right? So if it's good here and the value's green, that means I don't need to evaluate the rest of these because I know that they'll work. Okay? Now, what would be the next best place to do this? Well, I can always divide a certain portion, right? But I don't know if it's going to be the left side or the right side. So I should always split the system in half, right? So if I check here and I say, okay, this is too little time, it doesn't work here. Well, then that means if it doesn't work here, then it doesn't work anywhere to the left. Right, so I can split this system in half again. Now where would be the best place to check? In the middle here, right? Because I can always split one side. I say, okay, it does work here. So I can split this system in half again. Maybe we should do different colors here, actually. Right, because this red signifies actually anything here can be done. No. Then I split this system in half again, because remember, why are we splitting in half? Because we don't know which side is going to be the effect, right? If it works here, we can remove everything to the right. We can neglect that. If it doesn't work here, we can remove everything to the left and neglect that. So if it could be one or the other, the best place to check would be in the middle, right? If here it doesn't work, imagine that, then this side gets split. We say, okay, none of this is going to be it. And then we check here and imagine that this is the last value and it says it does work, or something like that. And now we're here. So what did I just do here? I took this system, I split it in half. I did an evaluation based on this formula. I said, does it work or does it not work? It does work. So I split it in half again. I keep splitting it in half. What does that look like to you guys? That's just plain old binary search. Okay? So if you have a problem where you're trying to find the smallest of something that works, like you're trying to find the least number of minutes that you can fix all the cars given the mechanics and their associated rank, it either works or it doesn't work on a value, right? Is it simply put where if I give you the number of minutes, can you tell me always if it works or if it doesn't work? And that's the case here, right? If you give me any minute value, I can evaluate whether or not we can fix enough cars in the minute value allotted and if it's greater than the cars provided. Okay, so I can figure out if it works, it doesn't work. And are you in a situation where if it doesn't work for a value, it doesn't work for any value smaller, and if it does work for a value, it does work for any value larger, right? So in this case, yes, I can, right? If you give me a minute and it doesn't work, if you tell me 10 minutes and I tell you it doesn't work in 10 minutes, then I can't do it in 9 minutes, I can't do it in 8 minutes, I can't do it in any time less than or equal to 10, okay? If you give me 50 minutes and I say, you know what, it does work for 50 minutes, I can fix enough cars in 50 minutes, well then I can definitely do it in 51 minutes and I can do it in any time greater than 50 minutes, right? So if I can't do it for a time, I can eliminate all those to the left, and if I can do it for a time, I know it works and I can eliminate everything to the right. So that's where this binary search approach always comes into play. So what are we gonna do here? We're gonna do binary search. We start with a low value and we have a high value. We check the middle. If it works, we eliminate everything over here and we look over here. If it doesn't work, we eliminate everything over here and we look over here. But with this as the kind of example, right? We eliminate it. We have our low and high values of what could possibly be the number of minutes. We check the middle. If it works, we eliminate everything over here. We look at here, we check the middle. It doesn't work, so we eliminate everything over here. We go over here, we check the middle. I lost count here. But you get the general idea of how this works, right? So let's go ahead and design the kind of generalized code for this kind of problem. And then we'll tweak it for this particular case, okay? So how does this code work? It's pretty simple, actually. It's a pretty generalized formula I'm going to show you guys, right? So we'll call that function f. And what is it given? It's given minutes. I'm just going to call it m, but generally m doesn't mean anything special. And then you run the function on the thing and you return if it's true or false based on something. If something's less than something, something's greater than something, whatever, right? What's the true condition that you could do it? Okay. And then all you do is you return 1 plus bisect left, the range of which you're going to test. So from your low to your high value. So that's the values that you could possibly think of being like, what's your low point? What's your high point, basically? Okay. So what's low? What's high? And you're looking for true. So you're looking for the place where it's true. And your key is that function. Okay. So this might look very weird to you, but I'm going to explain it right now in a moment. First, your function. Well, that's the thing that you evaluate to true or false. All right, so that's the minutes thing here. So what was our function in this example? Our function was the beautiful sum of the floor divide of m divided by r square root is greater than or equal to cars. Okay, so if we do the sum of the floor divide that you just turn to an int, that's the equivalent of floor dividing, of the square root of something. Sorry, it's always hard to do this. Of m divided by r, right? If that's greater than or equal to cars, that's our formula. And the beautiful thing of this, since it's so short, put it on one line. All right. Now, what are our low and high values? The lowest thing it could be is I could do it all in 1 minute. The highest thing it could be, someone in the comments actually helped me because I don't know what the highest value could be. What could be there's 10 to the 6 cars. let's just say 10 to the 15, but I really don't know what the highest value could be here. Okay. And then looking for true. R is not defined. Return sum of, okay, because this is sum in for R in ranks, right? So this is basically just a re-representation of this is the sum in code form, right? That little summation I made earlier. This is the same thing, but in Python. All right, and then we'll submit that. Right, but basically this general form will work for anything. And how does it work? This is a little complicated, okay? Basically what's happening here, right, is we're bisecting. So bisecting is trying to find the place where something belongs, okay? And what are we looking for? We're looking for true. So we're trying to, basically this thing will return, this, you can imagine this is like an array where it's always false, right? Because when it's red, right? Remember when it was red, that means false, meaning that it evaluated a false corresponding to, no, that's not enough time, right? And at some point, it'll be true, and then it'll be true forever, right? Because that's the nature of this problem, right? If it's true for something, if I can do it in an amount of time, right? If I can do it in an amount of time, I can do it in any greater amount of time. And if I can't do it for an amount of time, I can't do it for any time less than that, right? So basically what this code does is it bisects like this. And it has all these values that it actually hasn't evaluated the value for yet, all right? And then when it bisects, it'll start in the center and figure out if it's true or false, right? So basically, it'll bisect here. It'll run this formula and say, is it true or false? If it's true, it doesn't actually have to create all those values, but it can assume, okay, since this is true, it assumes that all these are true too, because that's the nature of this problem, right? If it's true for something, it's true for anything greater. So it doesn't actually modify all these values to true, but since it set this to true, it knew and knows that everything to the right must be true, because what it's really looking for is it's imagining an array that looks like this, right? And so on and so forth. So then it'll cut here in the middle. And then they cut here in the middle and say, is it true? No, it's false. So then they can assume everything to the left is false and cut here in the middle. And this is true and true until it gets to the point where it finds the actual bisect. So, and then 1 plus because it's going to be 1 offset because it's a 0 array. So move over 1. Okay. 0 point array, looking for an index, right? Not a value. So the index that's correct, well, first one is actually 0, so you need to move everything over 1. And that's where this 1 comes from. But this is a generalized formula you can use to solve all the problems that have those 3 conditions. All right, guys, I hope you have a time constraint. Okay, so let's say n is the length of ranks. All right. Well, it's hard. It's hard, actually, because we do have to, well, we don't actually have to create this range array, right? Because range is like a, what's that called? A generalized, generative object. So we don't actually need to create this whole array. So we don't like create something with 10 to 15 space, or this thing would fail because that's way too much space. So, but we need to evaluate and then move 2 pointers. So really we only have 2 pointers associated with this, right? You have a left pointer and a right pointer. Even though you create this 10 to the 15th thing, it's kind of misleading because really we just have a left pointer and a right pointer doing binary search. So that's constant space. Here we have constant space too, because we're just evaluating the sum of something and making a comparison. So in terms of space, as weird as it sounds, this is constant space, okay? What about time? Well, for time, what do we end up doing here? We go log, we do a log n binary search. So binary search is log n, but it's not this n. It's 10 to the 15. So it's log of 10 to the 15. Right, so it's whatever the log of your high and low is. Now, this is where programming gets weird because, I mean, this is where time complexity analysis gets weird because it is 10 to the 15. It's log of 10 to the 15, but that's technically constant. But 10 to the 15 is huge. So are you going to negate talking about that? So since it is constant, but it's so large that I feel like it needs to be stated in your runtime complexity, even though it is technically constant. So it's log of 10 to the 15 because you're doing a log operation on the space from 1 to 10 to 15 to try to find the optimal number of minutes to do something. But then every time you do that log operation, you need to determine if your solution works. So you have to look at all n elements to determine, okay, I have n ranks. Let me figure out if this works for the given minutes. So every log operation, you have to do n operations to figure out if it works. So that's times n. Okay, so that's big O of log of 10 to 15 times n, which is technically big O of n if you call that log term a constant, but that's a little bit weird. Okay, guys, I hope you have a beautiful rest of your day. Bye-bye.